recording now.
I believe she's on now. Dr. Espaillat?
Yes. Hello, I'm here.
Hello.
Hi, we're going to make you a co-host.
Okay, sounds good.
You can share your slides here.
Great. I'm getting set up, so give me a minute or two.
Sure, take your time. Thank you.
Can I start sharing my screen now?
Yes, I'll give up. Let me stop sharing, and then you can have it.
Great. Continue. PowerPoint, share. Let's go over here. Okay.
I see it.
Great.
Looks like it's working.
Great. Okay. All right. I think I'm set up on my end here.
Great. Thank you. Derek, we should probably think about putting some of that, ambient planetarium music on it, at the beginning while we're waiting. Set the mood.
Yeah, I'm just I'm trying to figure out. I'm trying to see. I need to get a mixer. What I need, so that way I can just make one channel of music. So that way you don't hear my notifications going on in the background.
Bing.
Exactly.
Well, it's 7 o'clock. We should probably go ahead and get started. I can't see.
It looks like it switched back. Let me try that again. Okay.
Are you good? So I'm going to talk. I did switch back. I'm going to talk for a few minutes and then let Tricia introduce you, and then we'll go back. We'll go back to you.
Okay. Okay.
Okay. I won't ramble too long. So we'll go ahead and get started. So it's 7:01. Welcome to the November meeting of the Central Florida Astronomical Society. I appreciate everyone's continued patronage this year as we've been meeting on Zoom due to the not to be too cliche, the current situation, so to speak. We have a great meeting, I think, planned for you tonight after my announcements and upcoming events. We're going to have a talk on baby planets from Professor Catherine Espaillat. And no, I said baby planets. And then we're going to have a talk on Alpo from Bill Castro. Derek will be showcasing some of our members' photos and sketches. I'll be spending just a minute on the moon, and Derek will also do our Tonight Sky and Observing report. And then finally, we'll have our new mini program on astronomy history by Taryn Hill. Just a couple of reminders. Our official communications through CFAS is now on Groups.io. We do still post on Facebook and Twitter and all of that, but Groups.io is the official central place for all things CFAS. If you're not a member, you should go ahead and sign up. It's, of course, free, and we don't spam you or track you between websites and all that sort of thing. We have a new publicity chair, Sharife Gazelle, and she asked me to remind you that she is looking for astrophotos from members to use in her social media efforts. These do not have to be this week's astrophotos or this month's. Just send her your best astrophotos that you wouldn't mind sharing, that she could showcase as work that's done by CFAS astrophotographers, and her email is down there at the bottom, sgacel@gmail.com. Also, last month we talked about the Royal Astronomical Society Observing Guide. We did not have enough people who had expressed interest at the time, but we do now. We have 14 copies that have been ordered. We don't know when they're going to come in, but when we do, we'll announce on Groups.io that they're here, and we'll make some kind of arrangements for people to come by somewhere and pick them up. We did also order enough calendars. Not everybody said they wanted a calendar, but we went ahead and got enough calendars so that anybody who wants one can also get a calendar. Also, I want to recognize our star member, Bill Castro, who got another award this month. This is from the Astronomical League observing program doing variable stars. CFAS has a rich history in variable star observing, actually going back to our founding 40 years ago. So it's really great to see Bill, along with, and I know Barbara Harris is also still very involved in doing variable star observations, but that's really great as well. Upcoming this month, if you missed it, we had a great Picks and Sight class yesterday hosted by Frank Kane. I was there for about an hour before I had to leave, and we had about 15 people online, and Frank did record it. It's at the Ort Uta de Makafa, whatever that is. You'll have to catch that real fast. It is on the Groups.io mailing lists, so if you don't get it off of this slide fast enough, or you don't do a screen capture real fast, quick print screen, there you go. Also, we're having a star party this weekend. Oh, it might be Saturday, it might be Friday. Who knows? There's a drunk hurricane out in the Gulf that can't make up its mind what it wants to do. Derek's going to talk about that with his part of his observing report later when he talks about night sky, and we may take a poll and see what people are most interested in. We do have one virtual outreach event going on this month, and that is Galaxy Quest, hosted by our member Mark Gillette on his YouTube channel, and here's the URL for that as well. And that's all I have for the pre-show. I'm going to let Tricia introduce our guest speaker, and then I'm going to be real quiet for a while, and we're going to hear about baby galaxies and stuff. So Tricia, take it away.
Thank you, Richard. So welcome, guys. Tonight we have Dr. Espaillat joining us. She studies how young stars and planets form at a protoplanetary disk. She is particularly interested in characterizing the footprints that protoplanets leave behind, and she uses multi-wavelength observations in her research. Currently, she is an associate professor of astronomy at Boston University. Before starting at BU in 2013, Dr. Espaillat was an NSF Astronomy and Astrophysics postdoctoral fellow and a NASA Carl Sagan Fellow at the Harvard-Smithsonian Center for Astrophysics, which, side note, a former member of CFAS, a young woman named Jasmine, she once did a tour of duty there. She was actually working there for quite a time, so kind of a CFAS Harvard-Smithsonian connection center there. Dr. Espaillat earned her PhD in astrophysics from the University of Michigan in 2009, and she received her BA from Columbia University in 2003. So let's all virtually welcome Dr. Espaillat to the Central Florida Astronomical Society. Clap, clap, clap.
Give me a second here. All right, so thank you for the invitation to come speak today. And also happy Veterans Day. I deeply appreciate all the veterans who have served our country. So thank you also for everyone in the audience for just coming and spending some time learning a bit more about baby planets. I love baby planets, and I'm very happy to share what we know about them so far. So just so you know, I have my chat open. So if you have questions during the talk, feel free to just pop them in the chat room. I'll keep an eye on it, and I'll address them as I see them, or you can unmute yourself and ask a question, or you can hold your questions to the end, whatever you prefer. I'm very flexible. Okay, so let's get started with the talk. So my research centers around one of the fundamental questions in astronomy, which is how do planets form? if we want to understand how planets form, we have to look at where they form. So another way of phrasing that is if we want to learn more about baby planets, we have to learn more about the nurseries. And the nurseries out of which planets form are called protoplanetary disks. And one protoplanetary disk is imaged here. So these are disks that are made up of dust and gas. And the generally accepted picture is that dust particles in the disk will collide with one another, stick and grow, and they'll form larger and larger bodies. And eventually these building blocks will form the cores of gas giant planets and also terrestrial planets. And then the cores of giant planets, they will accumulate the gas in the disk, and that's how they get their gaseous atmospheres. Now, as the planet is growing in the disk, we think it carves out a gap, like what you see in this artist illustration here. Now, that's the picture, that's what we think is happening. Now, the details of all that is not clear. And it's important to understand the details of how we get from this artist illustration to this other artist illustration, which shows us the amazing diversity in planets that have been detected to date. So you may have also heard of these called as exoplanets, so planets outside of our solar system. Now, one of the most striking results in the field of astronomy so far is this diversity. So there are over 4,000 confirmed exoplanets and over 3,000 candidates that are awaiting confirmation. And the planets that have been detected are diverse in size, composition, and also the architecture of the planetary system. So for example, we have one system where there are 7 small terrestrial planets packed within a radius that corresponds to the orbit of Mercury in our own solar system. And we know in our own solar system, we have rocky and gas giant planets. But here we've also seen in the exoplanets, worlds that are predominantly water, planets that are predominantly lava, super Earths. We don't have super Earths in our own solar system, we just have Earths, mini Neptunes, Jupiters, which we do have in our solar system, and also super Jupiters. So there are other kinds of planets out there that we don't have in our own solar system. So how do these diverse planets form? So we have to look at the protoplanetary disks. We have to look at where did they form from, because that's where all the material that went into making the planets, that's where it came from. And most stars, we see evidence that most of them were surrounded by disks at some point. So it's a logical place to look. So where to look is the easy part. Looking for the planets themselves is very hard. So it would be great if we could directly, take an image of a protoplanetary disk and image its planet. But that's really hard to do because planets, they scatter the light from the star. So some of them, when they're very young, they have some thermal emission that they generate themselves. But for the most part, they're just scattering light from their host star. Now, the protoplanetary disk around the planet is also scattering light from the host star, and it also has its own thermal emission. So it's very difficult to see a teeny tiny planet against this huge protoplanetary disk. So an analogy is, let's say, we're down in Florida and we're trying to detect a ballpoint pen going around a grapefruit that's in San Francisco. Okay, so that's hard. And now let's just throw in some dust in there to complicate things. So that's an analogy for what we astronomers have to do to try to detect planets and disks. So instead, we look for something that's easier to see. So indirect evidence. So the footprints that planets leave behind as they're forming in the disk. So theoretical simulations tell us that as planets are forming, they should be interacting with the protoplanetary disk, accreting material onto themselves to grow, clearing out gaps in the disk as shown in this illustration. So gaps in disks are one footprint to look for, and we have detected hundreds of disk gaps to date. So in this presentation, I've ordered the subsequent slides based on these 3 questions. So the first is, where did our solar system come from? How much do we know about protoplanetary disks? And what do baby planet footprints look like? So I'll be showing you here some images of what we've seen. Okay, so starting off with question 1. So where did the solar system come from? So we probably formed in a molecular cloud like this one that's imaged here. This is the Orion Nebula cloud that is located within the Orion constellation. This is 1,400 light years away. So it takes 1,400 years for light from or the Orion Nebula cluster to reach us. Now, this cloud is 99% gas and 1% dust. And each dot that you see here in the cloud is a baby star. And there are hundreds of these little dots in this image. So there are hundreds of stars. And the gas and the dust that's in the molecular cloud is being illuminated. The reason we see it is because it's reflecting and scattering light that it's receiving from these young stars that are within the cloud. Now, all of this is real data, and this is taken from by the Hubble Space Telescope, and this is my favorite image from the Hubble Space Telescope. So if we zoom in on these little dots in the Orion Nebula cloud, we see evidence that there are protoplanetary disks, and some of these protoplanetary disks are still embedded in their natal envelope or cocoon. And I'll come back to this in detail a little bit more later in the next slide. But there you just see some beautiful images zoomed in on what these stars surrounded by disks look like. Okay, so those were observations, real observations from HST. Here's a schematic of what's happening. So we start off over here in the upper left with a molecular cloud, and it contracts via gravitational collapse. Now, this is a process we still don't understand. Why does the cloud collapse in the first place? But we see the end result. There are stars, so it must have collapsed. And this is its own very active area of research. And we get a dense clump that forms, and then a star surrounded by a protoplanetary disk. Eventually, the disk dissipates, and you're left behind with the star and the planets. So you see that the planet traits are inherited from the protoplanetary disk, and the protoplanetary disk traits are inherited in turn from the molecular cloud. So where did the molecular cloud get its material from? So this goes back to Carl Sagan's quote, "We are made of star stuff." What does that mean? So in the Big Bang, only hydrogen and helium were created. Everything else was formed in the cores of stars. So carbon, oxygen, the laptop or the computer that you're watching this on, that I'm speaking into, everything was formed in the initial elements were formed in the core of a star. And the planet, us human beings, we're all formed in the cores of stars, our initial elements. And what happens is that there's a galactic recycling process. So let's start off with here, where we have a star, and this is an example of a high mass star, and in its core, it's burning, it's converting hydrogen to helium, and then helium to carbon, carbon to oxygen, and then heavier and heavier elements. And then at some point it reaches iron because of some physics. Iron cannot be fused within the core into heavier elements. And so the star explodes and you get a supernova. In that supernova explosion, all the elements heavier than iron are created. Now, supernova explosions are some of the most explosive, energetic events that we know about in the universe. And so the star is essentially spreading its guts over the part of the galaxy that it's a part of. So then, depending on where the star goes off, usually these stars go off in the midplane of the galaxy because they're young. If you have questions about that, you can ask me later. And within the plane of the galaxy, there are lots of molecular clouds. So these, as these stars go supernova, they're going to deposit all these heavier elements into molecular clouds, and they're going to seed those molecular clouds. And then the material in those molecular clouds is going to make it into protoplanetary disks and the central star. And then the material that's in the protoplanetary disk is going to make it into planets. And then eventually the star is going to, if it's a high mass star, it's going to explode and go through this process. Our own sun is not going to go supernova. It's not massive enough for that. It's just going to shed its outer layer. So it will be contributing some carbon and some oxygen back to the surrounding parts of the galaxy. Okay, and then there are two major types of planets. Terrestrial, we're on one of those. And then there are Jovian planets, also called gas giant planets. Terrestrial planets are small. They tend to be in the inner part of the solar system. And also when we look at exoplanets, they tend to be close to the star. They're made up of metals, rocks, and they have very few moons. Our moon is an outlier. It's abnormally large for the size of the terrestrial planet it goes around. So the Jovian planets, the gas giant planets, they're large, they're located in the outer part of the solar system, and they have a lot of gas, and they also have lots of moons and rings. And in our solar system, we have 4 terrestrial planets, 4 gas giant planets, and all exoplanets to date are either one or the other. Now, there are some differences within the classes, but they're either terrestrial or a gas giant planet. So that's telling us something, that's telling us that there's something fundamental there, that we only get 2 kinds of planets. And for the most part, the terrestrial planets that we see are close to their stars, and the gas giant planets that we see are far away from their stars. And so it's not a coincidence. It must be linked to something fundamental. And we think it's linked to the protoplanetary disk. So very close to the star, the protoplanetary disk is very hot. And as you get further away from the star, the protoplanetary disk gets cold. So when you're close to the star, you cannot form icy materials. And when you're farther away from the star, you can have ice. And ice is important because we think if you get a dust grain that's coated with a layer of ice, it makes it stickier. And if it's stickier, that means that things in the outer disk, grains in the outer disk that are coated with ice, they can coagulate more efficiently and form larger rocky cores, which can then go on to attract the gas in the protoplanetary disk. So for example, Jupiter's core is thought to be core is thought to be 10 to 20 times the size of Earth. So in the inner part of the solar system, it's too hot for icy grains, and so the planets don't get that large. Now, someone asked a great question in the chat room. What about hot Jupiters? I was avoiding hot Jupiters, but I'm going to go ahead and answer that question. So I did say most terrestrial planets are in the inner disk, most gas giant planets are in the outer disk. Now, there are some planets called hot Jupiters where you have Jupiter-sized things that are very, very close to their stars. And they caused a lot of confusion early on. Now that we have more statistics, we're finding that hot Jupiters are actually in the minority of planets. And there is some theory that says that maybe this is the fact that these hot Jupiters are close to the star is linked to some kind of initial conditions of the protoplanetary disk where they migrated inwards. So depending on how many planets you have and how they're interacting with one another and where they are in their radii, planets can actually fling each other out or fling each other in to the star. So hot Jupiters may be a case where maybe there was another more massive planet in the outer disk. To conserve angular momentum, one got flung out, one is migrating towards a star. And there are many different scenarios where you can end up with that. But that's an excellent question. Okay, so now moving on to the second question of this talk, how much do we know about protoplanetary disks? So this, we have to learn about protoplanetary disks by looking outside of our solar system. What I told you previously about the structure of our own solar system, that's the most we can really learn about our own protoplanetary disk because it's not here anymore, right? The planets are here. It did its job. So if you want to see protoplanetary disks in action, we have to look at younger stars that are still surrounded by protoplanetary disks. And what we've learned is that protoplanetary disks are complex dynamic environments. So here you have a schematic where the beige area corresponds to the part of the disk where you have dust and gas that are well mixed with one another. These arrows here are meant to show this process called dust settling, where you have small dust grains in the upper atmosphere of the disk. And remember here we're talking about a 3D object, so when I say the atmosphere of the disk, there's a top and a bottom, and they settle towards the midplane, the center of the disk. So the dust settles towards the midplane, and so you get a accumulation of dust grains here that facilitates grain growth. Like I said, we have a place in the disk where the temperature is cold enough for ice to form. So we call those snow lines. So we think that in our part of the disk, you can get very large planetesimals. As we get closer towards the star, you see these squiggly lines. That is an approximation of our knowledge about how does this stuff move in protoplanetary disks. We don't know. So we just put some squiggly lines there and we call it a viscous transport, turbulent transport. So it's still a very active area of research. We don't understand those details of how things are moving in the disk. Let's see. Oh, and then here on the right, you see an example of the temperature structure of the disk. So the hottest part of the disk is in red, the upper atmosphere and the inner part. That's because what's receiving most of the stellar emission, right? Because the engine of the disk is the star. That's what heats the disk. And then as you get to the outer parts of the disk and also to the midplane, that's where it gets the coldest. So that's where it's blue, that's where you can have some ice, and then you see some chemistry here in the different layers of the disk. This point here is labeled 1500 Kelvin. That's the point in the disk where the dust sublimates. So it gets too hot for dust to exist. It sublimates into gas. And this green transparent area here corresponds to the part of the disk that's just gas. It's too hot for dust. So it's just gas. And then these young stars that I'm talking about today, they have very strong magnetic fields. And the material in the disk, the gas in the innermost part of the disk, is attracted to the magnetic field lines, and it's channeled onto the surface of the star, where it slams onto the surface of the star, moving at hundreds of kilometers per second. And it forms a very hot accretion shock, which is this little purple circle here. So when it slams into the surface of the star, it generates a lot of energy. It's very hot there. Okay, so that's what our general big picture view of what protoplanetary disks look like. So someone asked, do you come across many first generation planets? If so, terrestrial or gas? I'm not sure what you mean by first generation, because we don't, so like for example, in our own solar system, there could have been other planets in our solar system that got ejected early on in the early formation of the solar system. So maybe the Earth is a second generation planet. It depends on what you call first or second generation. So maybe later on you can elaborate what you meant by that there, and we can come back to that later because I don't get the question. Okay, so next slide. Okay. So we have these complex protoplanetary disks. They have very different temperatures throughout the disk. So you can observe the protoplanetary disk at different wavelengths. Another question in the chat, why did Earth get lots of heavy elements, but the sun is mostly hydrogen? So that's a good question. So we think that the sun probably, so the part of the molecular cloud where the sun formed and the planets formed was the same part of the cloud. So it had the same makeup, but all of that heavier stuff probably sunk down to the core of the sun. So we can't see it. And it's such a minor part. So like, for example, the molecular cloud is 99% gas, 1% dust. In astronomy, when we say dust, we mean anything that is not hydrogen or helium. So there's probably much less than 1% of dust or heavier metals in the sun. They just sunk down to the core. And it's just such a small amount. There's no way we could detect them. Now, there was a follow-up about the first generation or second generation. So clarifying that by second generation would be after a supernova. So that leads into, there can only be, so with that clarification, there can only be one generation of planets. You have your protoplanetary disk, that sets the time scale at which planets can form. Planets cannot form after the protoplanetary disk is gone. So our solar system is not going to develop new planets at any stage in its life. Now, if the star goes supernova, it's probably going to obliterate the planets in the system. If a star goes nova, like our own sun, it's going to, not nova, I mean, it's just going to be in the red giant phase, and it's going to dispel its outer layers. Though it will be left behind with a white dwarf in the center that's still going to be surrounded by planets. And that's also an active area of observation where people are looking for planets around white dwarfs to see what happens to planets after the star expels its outer layers. And then someone asked, are you referring to first generation stars? No, here, definitely not first generation stars. Those stars were very massive, and they all died out very, very early in the formation of the universe. But those first generation stars are probably the ones that generated anything that was heavier than helium in the first place. So they did start the cosmic recycling chain. Okay, so in this panel, in this figure, the different wavelengths that I just want to point out different wavelengths because later on I'm going to be showing you images at different wavelengths. So, you know, in the UV, the ultraviolet, we're tracing the secretion process onto the star. So when I said all the material from the star impacts the stellar surface at high velocities, that emission comes out in the ultraviolet because it's so hot, it's so energetic. In the near infrared, we're seeing the innermost part of the disk. Specifically, we're very sensitive to smaller dust grains. In the mid-infrared and the far infrared, we're probing further out in the disk. And in the millimeter, we're probing the bulk of the disk and specifically the midplane of the disk and the larger dust grains, so approximately millimeter-sized dust grains. Okay, so I'll try to remember in the upcoming images to tie to each of the wavelengths that the images are taken in. Okay, so I can't do justice to everything we've learned about protoplanetary disks in one talk, so I'm just going to highlight what I think is the most relevant for planet formation. Now I'm going to step through these images in more detail one by one shortly, so you don't have to squint. I just wanted to show you a big picture of how much progress has been made. So protoplanetary disk research, for astronomy, it's a pretty new field. We've only been around for 40 years. The first evidence of protoplanetary disks was found in the early 1980s. And that's this image here in the upper left. And then here is what we have, some of the most recent results from some of the most powerful telescopes today. So I'll explain the differences, but you can tell just by eye what huge progress we've made in the past 40 years for this very young field. And how our capabilities are increasing. Okay, so let's step through these images. So these are images from 1985, and these are actually, so this is what's called a spectral energy distribution. So essentially it's a plot of brightness versus wavelength, where the wavelengths here are the optical bands, and then here we're going into the near and the mid-infrared. And what these researchers did is they took these photometry of these young stars, and they saw that at the shorter wavelengths, okay, it looks like a star, that's fine. But then at the longer wavelengths, the emission bumped up. And what they were expecting were these straight lines here. So what they found is this excess emission, extra emission at the longer wavelengths. And that's what I tried to shade in here in red. So that's more than you would see from just a star by itself. So this was interpreted as evidence that there was dust around the star. So dust the dust likes to absorb light at short wavelengths. The star emits most of its radiation at short wavelengths. That heats the dust up, and then it re-emits at longer wavelengths as it cools down. So it's gonna preferentially absorb optical light from the star and then cool down and emit this in the infrared wavelengths. So this was the first evidence that there was dust in a disk around a star. There was also some interpretation at the time that maybe this is chromospheric emission. It's coming from the atmosphere of the star itself, or maybe there's background emission in the molecular cloud. And it really wasn't until this image taken by the Hubble Space Telescope in 1994, where everyone got on board when they visually saw with an image that yes, there are indeed protoplanetary disks around these young stars. And here what you're seeing, these blobs are protoplanetary disks that are seen against the background of the Orion Nebula cloud. Let's see. Okay, so here are some more near infrared images that HST took in 1999. Now these are edge-on disks. So to guide your eye, here's a little cartoon of an edge-on disk. So you have your protoplanetary disk, the star is in the center, so you don't actually see the star, and you see this dark lane here. That's the midplane of the disk. So that's where the dust, there's more dust, it's more dense, so it's gonna be darker, right? Because the dust is absorbing light from the star and it remits it thermally. It doesn't reflect a lot of the light of the star in the midplane. But at the very upper layers of the disk, you can tell it has kind of this shape, and this light at the top and the bottom, that's being scattered off of the flared surface of the disk. So that's the artist's cartoon conception there. And then here are some actual observations, and I'll stick with this one, maybe this one, because it looks more like the orientation of the cartoon. So the protoplanetary disk is actually the dark part in the center. And then here you have light being scattered off of the top surface and the bottom surface. You also see a little bit of evidence there for a jet that's coming out from the star. Okay. All right, so then in the 2000s came the age of the Spitzer Space Telescope. So this is when I entered the field as a PhD student. And Spitzer was a space-based infrared telescope, and it gave us detailed wavelength coverage in the infrared. And we found that about 10% of protoplanetary disks have these large gaps of tens of AU. So, right, we're at 1 AU here, Jupiter's at 5 AU, Saturn's at 10 AU. So these were solar system size gaps in protoplanetary disks. And here's an example of how we got to that interpretation. So on the left is a star, and on the right is what Spitzer would see for a star. So just a straight line. Here's a star surrounded by a protoplanetary disk, and in red is what Spitzer would see for that case. And then here we have a disk that has a big gap in the center, and the red is what Spitzer saw. And you see that the short end of the spectrum here agrees with what you would expect to see from the star by itself. And then at the longer wavelengths, it agrees with what you would expect to see from the protoplanetary disk without a gap. So there's some emission missing here. So there's a hole in the disk. So the dust that is there in the protoplanetary disk without gaps and is emitting is not present in the disk that has a gap. Okay, now we have beautiful images taken by the ALMA interferometer in the mountains of Chile that show us that there are very small gaps in protoplanetary disks. So the sizes of these dark lanes here, these gaps, are about 2 to 5 AU in width. And not only are we seeing one or two of them, we're seeing a handful of them. So we see multiple gaps in these disks. And this is HL tau, so it's in the torus molecular cloud. And this is at the highest resolution of ALMA, which is an interferometer. It's composed of 50 radio telescopes. And this was is a revolutionary image in the field of protoplanetary disks, just to see so many gaps. And we think, what is causing these gaps? We think it's planets. And that leads to my next question for the talk, which is, what do baby planet footprints look like? So since HL tau, we've taken images of many other protoplanetary disks, and it's not the only one with small gaps. There are many more small gaps in protoplanetary disks. And then the question is, are these the footprints that small planets, as they're forming, or baby planets, they'd be gas giant planets. Are these the footprints that they leave behind as they're forming in the disk? So this is an artist's conception of a theoretical simulation of how a planet forms in the disk. It's thought that as the planet here is forming the disk and as it's going around, it's accreting material from the disk, and it's also clearing out a gap in the disk. So planets right now are the favorite leading hypothesis for how we get these gaps in protoplanetary disks. And here is another protoplanetary disk. This is the closest protoplanetary disk to us, TW Hydra. It's located at 40 parsecs, which is about 130 light years. So this is the closest protoplanetary disk to us. So we have a lot of observations of this object. And TW Hydra is the closest, so I said that it's the closest. And now you see here that there are many small gaps in the disk. And if you zoom in here, you see that there's a gap down at a radius of 1 AU. And that's very interesting, right? Because here we are on Earth at 1 AU, and we see a gap in a protoplanetary disk that has a size of 1 AU. This is a beautiful image. It's also a little bittersweet because most protoplanetary disks are not at 50 parsecs. So most protoplanetary disks are 150 parsecs or even further away. So we're not going to be able to resolve 1 AU, small gaps at 1 AU for most protoplanetary disks. So it's really just TW Hydra that we can do this for. Now, the fact that we saw gaps in HL tau, that was the first one, right? Remember this image, this one? That was pretty surprising because HL tau is actually pretty young. It's a protoplanetary disk, but it's still embedded within its natal little dense cloud that it formed out of within the larger molecular cloud. So here's what HL tau looks like in the optical. And you can see it's kind of a mess. You see these two jets coming perpendicular from the system. There's a lot of dust, dusty material around it. And way down in the center is where this millimeter image was taken. And you see this very serene looking protoplanetary disk. It looks very symmetrical, even though there are these very powerful jets and a lot of emission, a lot going on in the system. So, this got us started thinking in the field. Not only were the gaps very interesting, but also the age at which we're finding these gaps. So we are revising our theories about when we think planets form. So maybe they form a little bit earlier than we thought. We thought that planets would form when you just had a protoplanetary disk stage, when it was outside of its dense, the dense little cloud that it formed out of. So we see gaps at all stages. Okay, now here are the results from ALMA that I showed you before. They're just color-coded. Before they were purple, now they're kind of orangish. And here on the right, so these are millimeter images. On the right are near infrared images taken with the very large telescope, the Sphere instrument. This is in also the mountains of Chile. So I'm showing these side by side because ALMA in the millimeter is tracing down to the midplane of the disk. Sphere in the infrared is just skimming the top surface of the protoplanetary disk. And I love this beautiful image of this protoplanetary disk here, where you can clearly see that here you have the midplane, and then here you have it's kind of a bowl shaped, whereas before with the HST images from the 90s, you had to put that artist illustration to help you visualize it. And here it's pretty clear. You see the top bowl of the disk, and then you can't see the bottom bowl here because it's pointing slightly away from us. So aside from that beautiful flared structure, you also see lots of gaps in the millimeter and in the near infrared. So maybe all these disks are full of baby planets. And here we have an image in the near infrared, which is our first and only so far image of a protoplanet within a gap in a protoplanetary disk. And this planet has been measured to have a mass of 10 Jupiter masses. So the protoplanet is here. And let me step you through this image. So the very center is just a black circle. That's because the observers had to block out the light from the star. Everything else you see over here in like red, that's tracing dust emission. And you see that overall there appears to be a large hole in the disk, even though there's some material in it, but overall there appears to be a large hole, and it's or gap. And then within that gap, you have this bright continuum source here, and that's the protoplanet. So this has a estimated mass of 10 Jupiter masses. It's located, so the size of the disk gap is 54 AU. So for some reference, Pluto is about 50 AU away from the sun at its furthest point from the sun. So this is a very large gap in the disk. And this protoplanet is at 22 AU from the star, and Uranus is 20 AU from our sun. And this system is called PDS 70, and it's located 370 light years away from us. Okay, so that's the actual image. This is an artist's conception of what is happening inside of PDS 70. So you have the star here. So it's not artist's conception. They didn't have to block it out. You have some dust close to the star. Here you can make out that there's a protoplanetary disk at the larger, as you get further away from the star. Here you have the gap, and then here you have the planet. And you can see that the planet is still accreting material, it's still growing, and it's kind of acting like a funnel or a passage for the disk material to go through past the planet. Some of it accretes onto the planet, some of it makes it through and accretes onto the star. Right, so these protoplanets are still growing. That's why we call them protoplanets. Okay, now protoplanetary disks get a lot of attention because of planet formation, but protoplanetary disks are also surrounding very interesting young variable stars. And the innermost disk is a very complex environment. So you have here these streamers. We think that they're threading the magnetic field, and this is an artist's conception. So material from the disk is being channeled onto the star. You get very bright emission once this material impacts the surface of the star. And this is, I've done some research looking at gaps in protoplanetary disks. And most recently, right now, I'm looking at trying to understand this process of accretion from the protoplanetary disk onto the star a bit better. And to do this, I'm trying to tie together different parts of the star and the disk, which I told you before, those emit at different wavelengths. For one target, one young star with a protoplanetary disk, I've obtained data with all of these different telescopes coordinated in time, which hadn't been done before. So I got data with Chandra and Swift in the X-ray, that's tracing stellar emission. Data with the Hubble Space Telescope in the ultraviolet, that's tracing the material once it hits the surface of the star, so that hot emission. I got data with TESS, which is another space telescope, and it's in the optical wavelength, so it's tracing emission from the star, not very energetic emission though. I got, when Spitzer the Spitzer Space Telescope was still operational, I got some data with Spitzer in the infrared, and that's tracing material from the innermost part of the disk, so this edge here. And I also got data with ALMA. So ALMA is an interferometer, and it gave those beautiful images of gaps, but I'm interested in using ALMA to trace the molecular gas emission coming from the surrounding protoplanetary disk. Okay, and then, so I got that data. I got 3 sets of data looking at this star with simultaneous data 3 times, separated by a week, trying to understand more about how the star and the disk is connected. And this variability, studying variability around these young stars is a very active area of research, and there's a lot that can be done in the near future. So TESS is up and running, and it's still collecting lots of data for T-Tauri stars. The Hubble Space Telescope, it's going to be doing, starting actually in 2 weeks, a large survey looking at accretion in these young stars and collecting a lot of data for us. And there's also the Vera Rubin Observatory, which will be taking, once it's built and fully operational, it's going to be taking a survey of the sky multiple times. And many objects will be detected, of course, because it's an all-sky survey, multi-cadence, multi-epoch, but some of the brightest young stars will also be detected. And then, of course, we have the next generation of 30-meter class telescopes that's coming online, and they will have the resolution and the sensitivity that are necessary to detect many more protoplanets. So with 30-meter class telescopes, it's going to greatly improve. It's going to be a big technological leap, and it's going to make it much easier to detect more protoplanets in the disk, actually through imaging them. So to give you an idea, these 30-meter telescopes are going to give us a resolution of about 1 AU at about, in the near infrared, at the distance of many protoplanetary disks, which is 140 parsecs. I told you before, right now we can only do that for TW Hydra, which is the closest one. But when we jump up in resolution and sensitivity to 30-meter class telescopes, we're going to be able to get down to 1 AU for many more objects, not just the closest ones. So we'll be able to see with these facilities, very small gaps in disks. We'll be able to see spiral structure induced by the planets and disks. And we might even be able to see the shadows that planets cast on the protoplanetary disk behind them as they're going around the star. And then there's a lot of excitement about the James Webb Space Telescope. It's scheduled to launch on Halloween 2021. The first round of science proposals is due in a week and a half. It's taking up a lot of my time, but it's due the Tuesday before Thanksgiving. So a lot of astronomers around the world are going to be spending the next week and a half writing JWST proposals. I'm writing 2 myself. So the James Webb Space Telescope, JWST, this is an infrared telescope. So it's like a successor to the Spitzer Space Telescope, which I told you about earlier. It's going to be very powerful, and it's going to help us learn about the composition of disks. So on the left is what JWST is going to look like. And then on the right here is just an example of a spectrum. On the bottom is an example of a Spitzer spectrum, which was a low resolution. So this blue one here. And then going up are lines of different molecules, carbon dioxide, C2H2, H2O, HCN, and showing you the resolution of JWST. So JWST is going to have the resolution to be able to detect this forest of emission from molecular lines that our previous best infrared space telescope, Spitzer, just wouldn't be able to do. And of course, we're very interested in understanding water in protoplanetary disks, because the water on Earth had to come from the protoplanetary disk that the Earth formed out of. So we want to understand how much water is in these protoplanetary disks, so we can understand how did water get to Earth, because we still don't understand exactly how did water get to planet Earth. So to quickly wrap up, I just wanted to remind you that we've detected an amazing diversity of planets to date. And this amazing diversity in the planets, the exoplanets, is related to, I think, the amazing diversity of the protoplanetary disks that we've seen so far. So thank you very much for your time and your questions. I'll take any other questions now.
Thank you, Dr. Espaillat. That was really cool. Baby planets. Does anybody have any extra questions? Sounds like they asked them while we were going. You addressed them while you were talking.
Mm-hmm.
Okay. Yeah, thank you. Well, thank you very much for your time. And I wish you well as you work on your 2 proposals. Actually, while you were talking, I looked you up on Twitter. So anybody who wants to follow her exploits in protoplanetary disks can follow her on Twitter. I'll post it in the message thing. Probably during the next talk. And again, and you're welcome to stay, but if you need to go, we understand, of course, as well. So thank you very much.
Yeah, thank you for having me. I enjoyed it. Thank you. Yep.
All right. Well, our next program is going to be Bill, who's going to talk about ALPO. I'm a big fan. I'm actually a member of ALPO myself. So Bill, do you need a minute or two or a second or two or something?
No,
there you are. You ready to go?
Yes, I am. Let me share the screen, I guess. Host disable participant screen sharing. Okay.
So Derek will flip you back on.
Yeah.
It should be good, Bill.
All right. Thank you. And share, and hopefully you're seeing. Are you seeing my screen okay?
Yes.
Oops. That's the wrong. I don't want that. I want that one. And we'll go to presentation mode. All right. Okay, so it's another presentation I put together on the citizen science projects, and not to be confused with the dog food ALPO. This is on the Association of Lunar and Planetary Observers. And some of the club's imagers might want to consider submitting your images to them, and not just the advanced people, but beginners can learn a lot about observing planets as well. So you might be thinking, when you compare the club members' images to what Lewis and Go and Peach produced, you might think they're shabby at best. But from what I've seen of the club's members' images and the images on the ALPO website, the club's images are just as good, if not better, than what's posted on Alpo. And that's what led me to present this to the club.
Yeah, we rock. CFAS
Yeah,
rock.
really, even
CFAS
some
rock.
of my crappy images are good enough. And some of the ones are just phenomenal. And we'll get into how to do that later. But I'm not a member of Alpo. I'm not familiar with it as I am with the AVSO, obviously. So any members out there, or anybody knows something, feel free to speak up and add to what I've got. So because of that, the slides I've got are either copied text out of the webpage, screenshots, or emails from with the people from the Alpo organization. And this is their mission statement. I'm not going to read it all to you. Basically, they study objects in the solar system. This is a pro-am organization where amateurs can contribute to science. And observers are wanted. Beginners, intermediate, advanced, and professionals. So training is offered to become a better observer. So that's great for the beginners. And then this also adds to the advancement of astronomy. There's lots of observing programs, not just the planets, and we'll get into that a little later, but you work with a coordinator for a given observing program, and being on a volunteer basis, you can do as much or as little as you wish. So this is the first screen of the homepage. It has the current news and events listed. Note the navigation is on the top row up in there, and you got left and right columns with navigation there. On the left side, you can see the links to the observing sections here and the training program there. On the right side, you can see the links to images and archives. And I think the links to the Yahoo groups, I think that's obsolete. You have to contact the section coordinator to be included in the section's group IO listings. And as you scroll down, this is the second screenshot I've got of the homepage. And in the center, you can see information about the upcoming conference, and the keynote speaker here is Pranvera Hyseni. I hope I pronounced that right. And that's her telescope behind her. And the left column has links to additional information in the journal. So I've listed the observing sections here so you can see them a little better. I also grabbed some of the club members' images from our group's IO page, and I think Facebook also. And they'd be suitable for submission. And we'll see in the next couple of slides what I mean about the club's images are better than some of these posted on the ALPO site. But things that would be submitted, you know, solar flares, mediocre image I took of some sunspots. It's kind of nice to see some now that solar activity is kicking up. The lunar section, there's a Mars section. This would be great to submit. Jupiter is always good. Saturn, those are the main planets that you think of, but the other sections are, you know, remote planet section. There's a comet section. Here's a beautiful image of the comet, the recent comet we had. Meteors, meteorites. In the eclipse sections, not just the lunar and solar eclipses, but you know the images from the transit of Mercury. Those would be good. So moving right along, this is the Mars section page, and you can see from this it just has enough information. You can get detail on the planet. You know, like how big the ice cap is. Some of these things are highlighted. You may or may not want to do that when you submit your image. It's kind of up to you, but certainly our club's images are just as good, if not better, than and this one here. And then you can go to the web page for instructions on how to submit your image, and as time permits, we'll get into that a little later. And this is the Jupiter section page, and I scroll down to show the image from 2010. And this is kind of interesting. This was when the southern equatorial belt disappeared. So south is up, so that brown stripe belt there is gone. And when I first observed this, I thought I was seeing something, or maybe I whacked my scope on the way it set it up or what. I don't know what was going on. And I was happy to go to the ALPO page and confirm that neither my scope or I were whacked. Excuse me, the southern equatorial belt really did disappear. And that's the kind of information that's beneficial. Excuse me, allergies are kicking up. Visual observations are welcome as well. And it's not too far of a reach to turn our CFAS observing log, which we see here on the left, into an ALPO observing log, which is shown on the right. Pretty much the same information is on there, maybe a little more detail, and the training will tell you how to fill in the additional detail in the center, but it's, you know, your name, your location, time of day, universal time, and the equipment you're using. You know, in this case, a red filter and a blue filter, and you know, just a rough drawing. I think these numbers here, if I'm not mistaken, are the intensity, shading light or dark. I think 9 is very light, 10 is bright, I think, so forth and so on. So drawings are still needed. So I did some frequently asked questions with Tim Robinson with the ALPO. He's the Observer's Notebook podcast host. He's a training program coordinator. He's on the board of directors. And he also has Minor Planet 50718 Tim Robinson named after him. So that's pretty impressive listing there. And so why submit observations if, you know, Go and Pete are doing this? And basically they want 100% coverage around the clock, the moons and planets from its members. And they're not doing it 100% of the time. So, you know, images and as he reiterates, drawings are still in high demand. And do you have to be a member? No, you don't. They do give preference to members when publishing in a journal, but anybody could submit data. And what's done with the information sent in? So everything is archived. And ALPO has a very good relationship with NASA, and they have requested member observations of various solar system objects for use in their past. And then each section submits an apparition report to the journal for publication, and all the observers are noted and all the observations appear. And so how do you learn how to participate if you want to take it to the next level? Membership begins only at $18 a year, and members are free to participate in any section that interests them. There's some more questions on if you want to take this to the next level. Here's some information on the available training. And the training program is 2-tiered. The first tier is the basic level. It includes reading the ALPO's Novice Observer's Handbook and mastering the fundamentals of observing. So a lot of beginners or intermediate observers may want to try doing that, hone your observing skills. And the second tier is the novice level for further training, where one can specialize in one or more areas of study. You continue to learn and refine upon observing techniques specific to an area of study and assign a tutor to monitor your progress. And when that's mastered, you are certified to observer status for that particular field. And the last question we had is why join? And one, for me, it's not only to improve your observing skills, but you know, Tim replied to belong to an organization that values observational astronomy. And we're lucky to be in a hobby that allows for such a variety of interests to be explored. Excuse me. In addition, from Tim's own personal experience, having one's observations used as reference in a scientific paper gives you the satisfaction of accomplishment. And I can agree with that. I'll get reports or feedback from the AABSO that my observations were used in certain research papers and other documentation like that. It's nice to know that they're actually using what you send them. So with that, I wanted to show you how to submit the images. So I'll go to the web page, and up here in the upper right is Alpo image submissions. You just click on that, and this is it. Intro verbiage on top. It's as simple as sending an email to include your images in the archives. So you just attach it to an email and address it to one of these, Mercury, Venus, Jupiter, Saturn, so forth and so on, and send it in. Now they do want your image file name to comply with their format or convention from their gallery, and all the details are there. An example is right here, or here's the file name. And that's the information in that. Now you might want to get with the coordinator to see how you want to annotate information on your image as well. And then for more information, of course, you can go to the organization's webpage. Now there's a Sky and Telescope article online, Do Science with Your Astrophotography. It's by our very own Richard Wright. That was in Sky and Telescope. It's online, and that was written September 15th, 2020. Astronomy Magazine has Take Your Hobby to the Next Level by Mike Reynolds, and that article was in 2018. So if you have any questions, I would recommend contacting Tim Robertson, and his contact info is on the Alpo organization webpage. And scroll down to the bottom and you can contact him there, or you can just get a hold of me. So that's all I have for that.
Thanks, Bill. The only thing I would add, it is very inexpensive to join, and look through. I don't read it cover to cover, but if you're interested in the moon, there's a lot. I've learned all sorts of things about the moon from that journal. So if you're interested or anything, the journal also has a lot of very nice, a lot of good material in it for you. So thanks, Bill, for putting that together too.
Sure.
Okay, so next up on deck is going to be Derek with our members' astrophotos and sketches. We do have a number of very talented astrophotographers in the club, and some great sketchers as well. So every month, Derek likes to send them into Derek every month, and we'll show them to the other members. Even if they're not very good in your mind, don't be bashful about sharing. Everybody starts in the same place on the experience train. And you may think your work is terrible, but it may actually be very inspirational to somebody else getting started. And we're often, our worst judges when it comes to judging our own stuff. So I encourage you to send it in anyway, please. All right, Derek, I'll shut up now.
All right, thanks, Richard. All right, so like we do every month, we're going to go through a series of images. Not too many images submitted this month. Unfortunately, the weather hasn't been very cooperative, but we do actually have, we decided to kind of combine both sketches and astrophotography, because I think, in my opinion, sketches sometimes even take just as much work or even more work sometimes than astrophotographs, because of just the amount of detail and the amount of concentration and things like that are needed. Now, Bill Castro has been our super sketcher for the past couple of months, and as you probably recall, if you've been attending some of these meetings over the last couple of months, you've noticed that I've been doing observing challenges every month, and we have some observing challenge results here with some of Bill's sketches. So the first one I want to show here is Bill Castro's illustration of the double cluster of Perseus. So this was fairly not so great. Transparency was on average, using a 130 millimeter APO refractor, focal length of 910 millimeters at f7. Very nice sketch there. I think that he did a really great job with kind of rendering a nice wide field view of the double cluster using a 22 millimeter eyepiece. So a great there. A lot of interesting description there. Lots of stars. I think that's fairly accurate for this object. If we're going to have a few words to describe this object, it would be lots of stars. So thank you, Bill, for that. We're going to show Bill's next sketch. This is of the Pleiades, M45 there. So here we have, again, using the same refractor telescope and using a 31 millimeter eyepiece this time, so a much larger field of view. There are lots of stars as well in this object. So again, you can see the most common area here of the Pleiades, but of course, a part of that major cluster, there are a lot of other young stars there too. So a really nice, great illustration there, Bill, of the Pleiades. So thank you so much for submitting those images, and we look forward to doing some more in the future. So again, of course, for those that haven't done it yet, you can download the CFAS observing log file folder. You can actually download that through the groups.io file area. You too can illustrate your own. Of course, as amazing as Bill is as an illustrator, you don't need it to look exactly this way. Any type of illustration, just so that we know that you've got to see something through the eyepiece is accepted. So honestly, I'm a horrible illustrator. I bet you a 5-year-old kindergartner can do a better job at rendering some of the things in the sky than me. So don't feel bashful on submitting some amazing sketches here that we would like to share with our membership. This next image here, I believe, is also from Bill Castro. Bill's been very busy the last couple of weeks. Bill, if you're on, if you can go ahead and talk a little bit about this image here.
Yeah, this is just some sunspots that came out. Retired and bored and stayed at home. Gotta have something to do. And so this is with not the best refractor. I have a 127 Explorer Scientific with the FCD1 glass and a Beta filter material. So I just clamp on to the cheap mini Colossal 26 millimeter eyepiece. And I put a Canon point and shoot camera with or maybe a 4x optical zoom in there, and just take a bunch of pictures and see which one comes out. I sharpen it a little bit and enhance the contrast. But that's about it. That's about as easy as it gets.
Excellent. And then did you mention did you mention a telescope you used?
This one was the Explorer Scientific. It's a triplet, but it has, the glass isn't all that great, so the sharpness isn't as good as what it is with the Stellar View, but it's still pretty good. It's pretty happy with it. And I had the Beta Planetarium film, Solar film material for the filter. Problem is that filter won't fit on my new scope. It's too big of a cell.
Excellent. Yeah, well, it looks great to me, and it's very nice to see that there's a bunch of sunspots that are starting to emerge.
One thing, Derek, you had mentioned was trying to get the Thousand Oaks filter for my new scope, and I called them on the phone, and they're coming out with a new glass filter, and they're waiting for agency approval, regulatory approvals to start selling that. And so I'm on the waiting list for that, but that should be coming out. It's supposed to be better quality.
Excellent, yeah. And of course, refractors, Herschel wedge is the ultimate imaging for contrast and whatnot. But yeah, I'm excited to see those Thousand Oaks glass filters come onto the market and get a chance. So thank you, Bill, very much for these. We're going to move on to our next image. The next image is from Richard Wright. We're going to head from the sun to the moon. So Richard, I'll let you discuss this one here.
This is the crater Copernicus and the mountain range Montes Carpatus, or the Carpathians. So last month, the Minute on the Moon, I talked about this mountain range in the home of Castle Dracula for Halloween. So I don't remember the date. This was a few days before Halloween, while there was still quite a bit of relief on the moon when I shot this, and I used a 12-inch Newtonian reflector and a ZWO something. I think it was a 178 color camera.
All right, excellent. Yeah, very nice, sharp image there. We had some good seeing right around Halloween, so excellent, Richard. All right, the next image is an image I took of the ISS transiting the moon. I drove out to the Cala National Forest in wee hours in the morning to capture this flyby. Good seeing, 5 out of 5 seeing, so I really wanted to take advantage of that. So what's really cool about this photo I like is because this was taken during the 20th anniversary of the ISS, the continuousness of the human use of the ISS, but right next to it is the Sea of Tranquility. So I like the fact that we have the first sight of the lunar landing missions, Apollo 11, with the ISS here. So this is a zoomed in shot of that to kind of give you some detail there. Unfortunately, this was taken with a CPC 1100 HHD and a Canon 5D Mark IV at 1/4000th of a second.
So Derek, with SkyCal gone, how are you predicting ISS passes in front of the moon?
I'm using a software called ISS Transit. I can look at the link, and maybe I could do a mini program one day, or one meeting about that, or maybe even a workshop in the future on how to do this. It's quite tedious because unfortunately the center line is so small that you really have to be up to driving to sometimes an hour, 2 hours, 3 hours just to get to a spot that may potentially be lucrative. It rarely ever hits right near where you live. So that's one of the biggest goals with this, is that you have to be willing to travel to it. There was supposed to be an illuminated ISS pass yesterday, but ETA decided that it didn't want to.
Other plans for us.
Other plans. So hopefully in the future, we get a chance to, that's my next goal, is to get an illuminated ISS pass one time. So. All right, next shot is Richard actually sent this right at the beginning of the meeting. So he realized he had a really awesome picture of Mars.
Mars. Yeah, so this was taken same night as the Copernicus photograph, actually. Same 12-inch aperture. Newtonian aperture is king when it comes to planets. This was not at the native focal length, though. This I put in a 2x Barlow, so it was about 2400 millimeters focal length. I tried with the 4x, and the seeing just wouldn't support it, but at 2x it came out pretty nice, pretty usable.
Yeah, I think it looks great. I mean, it's Mars, and you can see the Valles Marineris and everything in there. That's pretty cool.
Yep.
All right. And the last image for tonight is an image of Jupiter I took. I was out for 3 hours on Halloween night doing observations with trick-or-treaters. I had a projector screen set up for social distancing. My neighborhood did a really great job at sending an alert out saying, these are practices that we recommend you do. And everybody in my neighborhood, anyways, my street, practice it really, really well. So I got a chance to show people Jupiter through the telescope, and then Mars and so on. So I didn't have a chance to really capture Mars or Saturn that night because we got a lot of people showing up. But kind of at the beginning of the event, I was able to look at Jupiter, so I decided to take a couple of shots. And here we have Jupiter with the famous Great Red Spot and the moon of Io. So nice. So this was with a ZWO 174 camera, color camera with a CPC 1100 Edge HD. So yeah, so a lot of planetary stuff this month, so it worked well with the Alpo thing. So I think we gotta start submitting some of our photos. But of course, we're hopefully going to be entering observing season very soon. So hopefully, we'll see more images from our members in the future. So, and that's all I have.
All right, thank you, Derek. So next up is we're going to spend a minute on the moon. Let me get my presentation going. It's not this one. It's this one. So my minute on the moon this month is Mystery on the Limb. I actually enjoy full moon or close to full moon. Right along the limb of the moon, there's quite a few interesting things that pop out that you don't see a lot of times. And so the night before Halloween on Friday, again, I had my 12-inch Newtonian out, and this time I did use a 4X PowerMate. I was pushing it as far as I could. And we've all seen these trenches like Valles Apples here, this 100-mile long trench. But when I was surfing along the edge of the moon on the western side, I saw this trench. And I don't remember ever seeing this at the limb of the moon before, this big giant trench, like somebody took a big gouge out. And it took me a few minutes to realize what it was I was looking at. So if you turn this sideways, which is more the orientation it was, you can see right here along the edge of the moon, and it's right here on this spot. Get my mouse over there, right along. That's yeah. Okay, there we go. Right along here on the edge, there's just this feature popping out that looks like this big trench right here. And so what is that? If we zoom in a little bit, we can see a little more detail. I used Lunar Reconnaissance Orbiter data to do this little rendering here, but I've got, if you move around the moon just a little bit, you'll see this large feature just out of sight on the western side. And what happens is the moon, it doesn't actually rock. It does rock, but it's only a few arc seconds, minutes physically. We have this thing called libration, where the moon, you can see more on the left, west and more on the east. It also works on the north and the south. There's actually 3 types of librations. The most prominent is called optical, because it's really just an optical illusion based on where you are and where the moon is on its elliptical orbit around the Earth. But we can actually see about 59% of the lunar surface because of these effects. And this month we had a very favorable libration for this large feature on the west side of the moon. We zoom in a little more. This is called Mare Orientale. It's a big ringed bullseye, if you will, and it's 183 miles across. It's a very, very large feature. As far as Maria goes, it's not very large, but as far as a crater feature, it's actually quite an incredible sight from the side of the moon. Its name means Eastern Sea. It was first discovered or observed the same way I observed it the other night by a German, Julius Franz, who described it in his book, creatively entitled enough, The Moon, in 1906. And he called it the Eastern Sea. Why is it called the Eastern Sea when it is on the western limb of the moon? Well, it turns out that through most of history, east and west of the moon is reverse of what we today consider east and west of the moon. We used to consider the eastern side of the moon to be the side of the moon that pointed to our east when we were looking at it from Earth. But in 1961, the International Astronomical Union changed that. They said, we're going to be flying to the moon and navigating and landing on it. We should treat it like it's a real planet or something. And so north, south, east, and west are going to work the same way they are on Earth. And so now when you look up at the moon, west is now on the left, and east is now on the right when you look at it. You can actually find a lot of old books and charts, because this was just 1961, and it's not like everybody changed overnight. but it's actually quite easy to find some old references to the moon where the east and west are reversed like that. So your November lunar challenge to look at the moon is actually just look at the moon with binoculars. And I was inspired because I got a new set of binoculars this month. So look at the moon with binoculars. It's amazing how much detail you can see on the moon versus naked eye. You can see quite a bit of features. Draw some sketches of the moon with binoculars. Label the features that you can see, and watch it throughout the month as it changes and goes through the phases, and see how that works. I love observing with binoculars. I remember as a kid always wanting a telescope, and you read in the magazines, well, if a telescope's too expensive, get them binoculars, they'll be happier. And I'm like, baloney, I want a real telescope. And for years, I went kicking and screaming before I finally got a good pair of binoculars. And I really, really enjoy binocular observing. And my last pair got stolen, so I got a new pair. And so I'm going to be trying it out on the moon this month, and I may even draw some sketches. And I hope you will join me as well. And that's it. That's a minute, maybe even a little more than a minute on the moon. So we're going to go back to Derek, and he's going to talk about tonight's sky and our other observing challenges, and talk about the Club Observing Report and what may or may not be going on in Geneva this weekend. And I'm going to stop sharing, quit talking, and let Derek take over. It's all yours.
All right, thanks, Richard. So we have a couple of objects that I want to talk about tonight. So we're kind of entering the closer. We're getting closer and closer to the winter months, but I'm going to set the time to about 9 o'clock. And one of the eastern and northeastern side of the sky is going to be our highlight of today. We can start seeing several constellations start to rise. The observing challenges are all going to actually be part of one constellation this month. So one of the things you're going to notice is if you look towards the east, around 9 o'clock, you're going to, of course, see Taurus, the bull, nice up, rising in the sky there. Of course, we have the Pleiades, which we looked at earlier, which is located just above the bright reddish star Aldebaran, which literally means eye of the bull here. So these stars make the Hyades star cluster. That's the head of Taurus. And then we have one object here for one of its horns and another horn right here. And next month, we'll probably do an observing challenge of one of the objects found here as well. But for tonight, I wanted to focus primarily on the constellation of oh gosh, it's been a long day. Auriga, there we go, Auriga. Wow, it's been a long day for me. Doing all programs all day, but Auriga, the charioteer here. A lot of people, when they see this group of stars, it doesn't really look much like a chariot. But the best way I see a chariot here is actually right here. You can see kind of where the person would be holding it, and then down here is kind of where the ground would be, and you kind of want to use your imagination for a wheel. But and then this is the person's head and his body here. So again, really stretching the imagination. But what a lot of people notice here is they notice these 5 bright stars here that make essentially a pentagon shape. So here we have the pentagon of Auriga, the charioteer. This area here is actually called the goats, and also this is called the gazelles. So different cultures have different words for this group of stars here. But again, according to mythology, Auriga was supposed to have saved a group of goats and was placed in the sky. But one of the things that we want to look at inside of Auriga, well, first off, we're entering the Orion spur of the Milky Way. So the Orion spur of our Milky Way kind of juts out at this time of year. And what we'll notice is that when we look closer towards Auriga, we'll see 3 distinct open clusters of stars. We have M38, or 36, 37, and 38. These are all 3 star clusters, all pretty much in the same area of the sky here. And what we'll do is we'll go ahead and to make it a little easier for me, I'm going to go ahead and center on the first one here, which is M36. and this is called the pinwheel cluster. So this is the first one we'll look at here, M36. All of these are open star clusters, so easy to see, especially with a small telescope. So you don't need something huge to look at these objects here. So don't worry and don't feel bad if you don't have a large telescope. I wanted to pick objects that were easily visible with a smaller telescope. And just south of M36 is M37. So we have M36 and there's M37. So we'll kind of zoom down here. Again, this is a much more denser star cluster as well. So again, two open star clusters. And then the last one we have this evening is M38. M38. And this one's a little bit further up. So as you can see here, we have these three distinct star clusters, M37, 36, and then 38. And M38 is the largest of all three. It's a much denser star cluster. So these are my astro observing targets of the month, are located here in Auriga. Now you can see that there's the flame star, and there's several other really nice deep space objects to photograph in this area of the sky. So there's definitely some interesting targets to get inside Auriga as well if you want to take that challenge there. So but first, as far as visual observing tonight or the next night is to look for those three distinct clusters of stars found in Auriga, and they basically are in a line throughout the Milky Way here. So now we have two bright stars in Auriga. We have Capella, which is the alpha star here, and Alnath, which is kind of the lower left side here. Those are the two distinct and brightest stars of Auriga here. So Auriga is going to be very prominent in this part of the sky at this time of year. And of course, just off to the right of it is Taurus, the bull, right here. So that's what I wanted to focus mainly on as far as objects in the sky. But let's just do a little quick review. Just above Auriga, right up here, we have kind of what I like to call a wishbone shape, and this is Perseus. Perseus, the Greek warrior, as they call him. And we have the nice bright variable star here, Algol. So again, once you find Auriga, just go straight above it, you'll find Perseus. And of course, what Bill Castro took recently is the double cluster Perseus, which is located just kind of off to the head of right over here, actually, right to the head of Perseus. And not too far from that is the Heart and Soul nebulas, which are great targets to look at for astrophotography. And as we zoom out here, and if we go from Capella, go straight up to Perseus, and if we continue straight from the double cluster, we'll get to the W or M shape of Cassiopeia, the Queen. So really nice area to look at. And of course, above Cassiopeia, we have the constellation of Andromeda right next to it with the Andromeda Galaxy. As far as planets right now, actually, we're actually able to see Mars, Uranus, and we'll also be able to see for a little bit here, left over is Saturn and Jupiter. What's really interesting about Saturn and Jupiter is, I believe on December 29th, let me just check one quick hot minute here. On December 29th, I think that's what it is. Nope, December 20th. I knew I was close. I'm actually going to go to the date of December 20th. And I believe it might be visible for a little brief period of time. Yeah. On December 20th, Jupiter and Saturn are going to be extremely close to each other. So it's conceivable with a wide enough eyepiece, or in this case, an imaging, you'll be able to capture Jupiter and Saturn in the same field of view, which is actually going to be really super cool. It's going to be very low in the horizon, so definitely it's going to be something you might want to capture just as soon as nightfall happens. Right now we're at 6:20 in the evening, so you definitely want a southwestern horizon. But on December 20th, we should actually have a really cool event where Saturn and Jupiter are pretty much going to be almost visually blurred together. So a nice conjunction, if you will. Now what I'm going to do here is I'm going to quickly stop my share here, and I'm going to go ahead and bring up Google Maps because I want to show you all the location of the Geneva Dark Sky Night happening this weekend. Now, I just recently checked the forecast while we were in the middle of one of our talks here, and it appears that Friday night happens to now be the clearer night. Saturday right now shows a potential chance of showers, and it's partly cloudy. However, right now, at this moment in time, Friday actually is going to be the clearest night. And so I wanted to gauge real quickly here. I'm actually going to stop my share for just a hot second. I'm going to bring up a gallery view. Just a quick poll. We have several members here tonight that are we're interested in going on a Saturday night. We decided it might be best to pick one of the two nights to do our observing. So if we were to move it to Friday to make sure that we actually do have a better night for observing, how many of you that were signed up for Saturday are able to do Friday instead? If you, all right. Okay, we have, so if you have, if you want to, yeah, okay, either do what Bill's doing and give me a physical thumbs up, or Eric can give me a reaction thumbs up. That would be great. Let me just kind of scan. All right, Asvin, okay, all right, excellent. Let me just kind of move around here. It doesn't look like, so right now, so what we'll probably do is, so far, several of the members have expressed interest. Okay, great. Andy is also giving me a thumbs up. I know we have several people that have given me a go-ahead for Saturday. Many of them have already expressed interest in going to do Friday. We're going to keep an eye on it, but right now, Friday looks to be the better night. If that changes, we can still do Saturday, but for those that aren't aware, I'm actually not going to be available Saturday. I'm actually having Eric be my substitute for Saturday night, but Friday I'll be available. So if it turns out to be Friday, that actually is going to be a better night overall anyways for me as well, but we can make it either night. But right now it looks like Friday is going to be the better night. Now, we have some questions about the Geneva campus. So let me show you real quickly. Here's the map. And you can see there's the Orlando Sanford International Airport. This is 46 right here. And we're basically going to take 46 all the way down to a road. Oh, that's a little too far. Called Osceola. All right, let me zoom in. There we go. I'm going to zoom in a little bit here. And what we're going to do is this road takes us all the way out to if we follow this road, it'll actually curve around and do all this kind of stuff. And actually, it takes you all the way to Lake Harney Wilderness area, and that's kind of where the landfill is. There's a dirt road right here, and actually I'm going to turn on the satellite for a second. There's a dirt road called Gun Range Road. Gun Range Road. It's not really. It's a loose asphalt road, so it's actually pretty decent. It used to be really bad. It used to be washboard. And it would be really a pain in the butt to have to drive on. They've done a good job with grading this road. And we're going to essentially take this road all the way till it ends. And you'll see it'll end at the Public Safety and Training Complex, which is the Geneva campus. So as you enter, you'll pass through a gate, which is located right around here. You'll pass a gate that will be open. And you're going to drive along. And eventually you're going to see a building with a parking lot next to it. That is the main building. We're not going to go there. Instead, we're going to, you'll notice you'll see this long driveway. We're actually going to turn, instead of going right into the parking lot, we're actually going to go left, and we're going to head down to this really large driving track. This thing is pretty large. It's actually over a mile long, or half a mile long, actually. So it's actually pretty wide. It stretches quite a bit. You can see how far it goes there. And this area here is actually where we're going to be doing our observing. This is really nice. There's no lights anywhere in this area. It's clear 360 degree field of view all around us, and very, very nice observing. For those that have been there already, you know that it's a very good location. The only stipulation with the site is that there is no power. So if you want to come out that night, you will need your own power. And then the other thing is that because we're doing this during time of COVID, we are going to ask everybody to remain at least 20 to 30 feet set up away from each other. If you do wish to visit visit people, we probably are going to avoid looking through people's eyepieces. But if you wanted to at least be social, we do ask that you wear a mask and to maintain social distancing practices of over at least 6 feet. Now, there is a restroom over here. It's actually in this building right here. It is naturally circulated air out from outside, so it's actually fairly good. But we do ask that if you do go to use the restroom, to make sure you are masked up. And that is to help with the safety and of everybody attending the event. So please, we do ask, we are given this very special opportunity to use this site. It's a very safe location. The nice thing I like about it is that it is, you're not going to have people driving in late at night. You're not going to have interesting people showing up all of a sudden. We just ask that you maintain those social distancing practices. We will have, if we decide to do it on Friday, we will have some red lights. We actually prefer that people arrive 1 hour before sunset to make sure that you get it's still bright outside enough to get in, see where you're going, set up, all that good stuff. And we'll be closing shop around midnight. So we'll have from sunset to midnight, which is definitely a plenty amount. Usually most people are done by then anyways. Usually the super dedicated are there till midnight, but that will be our call time for closing up for the night. So anyway, so that's what I have. If anyone has any questions, let me know. If there's anything else, you can just always email me any additional questions. I'll be sending a notification on groups.io, as well as the Facebook page for additional information about the Geneva Dark Sky Nights. So hopefully the weather continues to remain safe, but it is, as Richard said in the beginning of the meeting, this hurricane or tropical storm has its mind of its own. So we'll play it by ear. So thank you, everybody. You're muted, Richard.
Gosh, muted. So yeah, I was just saying thank you, Derek. So we'll leave it at that. Thank you, Derek. Okay, gang. So our last program for the night is going to be our new mini program on astronomy history from Taryn Hill. And I really enjoyed it last month, so I'm looking forward to see what he has to add this month. Take it away. I hope you're here.
Thank you.
Oh, yep.
Thank you. All right, going to share my screen here. See if I can't get to. All right. So I thought since we talked last week a lot of theory, we might look at a tool this week and see how it works. So start from first slide. I thought we would look at the history of quadrants. Well, not the history of quadrants and astrolabes, but in the history of astronomy, two tools that are probably some of the most fundamental. In this wood plate here from the Middle Ages, we have Claudius Ptolemy using a handheld wooden quadrant to measure the sky. Once again, I'm Charles Hill. This is just kind of a reminder of some of my bio information. And when we're talking, these tools are a major parts of the Ptolemaic tradition of astronomy. Before Copernicus came and shown us that the sun, that the Earth was not the center of all orbits, we had this Ptolemaic tradition where the Greeks, it started in the ancient Greeks and came through the Islamic world and was brought back to Europe during the Crusades and was continued in the early Renaissance. And this tradition of naked eye astronomy in the West is referred to as the Ptolemaic tradition. And it can roughly be found in the Alchemist here, which I have next to us. So reminding everybody of what the Ptolemaic tradition looked like for the universe. You had this Earth at the center of the orbits. You have this band here circulating around the Earth called the ecliptic, which is the apparent path of the sun and the moon, and it's also the band of the zodiac. You have this other band here called the meridian band that goes all the way around. You also have an galactic equator and the Tropic of Capricorn and the Tropic of Cancer. Above that, you also have the two Arctic circles. And this was conceived to be the giant skeletal structure of the universe. The whole circle is where the fixed outer band of stars would have been, and we would have seen the moon and the planets and the sun traveling around the ecliptic. And this would have been what the world was considered to be composed of in the Ptolemaic tradition. So if you're going to actually try to do astronomy, it's important to try to keep track of where all these stars are. There's several different methods of doing it. The most obvious method probably is to do the horizontal coordinate method. To get this, you need some sort of protractor or some sort of quadrant, and you find north, and north is 0 degrees. And then you measure from 0 to 360 degrees from the object, and then you use the quadrant to measure from 0 to 90 degrees, and this gives you a location-specific way of being able to determine where a celestial body is at a particular point in time. Now, this isn't good for very many locations, so we have other ways of doing it. The celestial equator coordinate method is one way, using the declination and right ascension. It is good for any location, and the declination is the angular distance above north and below the equatorial plane, and the right ascension is measured as the angle eastward along the equatorial plane, and the vernal equinox is at 0. With the ecliptic coordinate method, this is good for any location as well, and it uses, again, celestial latitude and right ascension. Moving on just a little bit here. Here we have two different kinds of quadrants. The quadrant on the left is a handheld wooden quadrant. It could be considered to be half of a protractor, and in a pinch you could use a protractor. You tie some sort of weight with a string to the center, and you can use it to determine how many degrees from the horizon something is. This big quadrant on the right is one of Tycho Brahe's wooden revolving quadrants, and it would be larger than a human. And so it would be easy to use for demonstration, as I suppose, but not as portable. So the quadrant is the first and most common medieval tool throughout most of the Middle Ages and the Renaissance, and even during the Greek period. The only more common tool than a quadrant would probably be the gnomon, which is just a vertical stick in the ground used to measure shadow plots. So after the quadrant, you have this tool called the astrolabe, and these things began in ancient Greece, and in the Islamic world is where they really became ornate, and we see lots of them in the Renaissance as well. On the front of it, you have this plate with all these spiky things on it, and that's called the rete. And under it, you have something that is built for each individual latitude location, and that is called the latitude plate. Oftentimes, there is a rule attached to the front to help you line things up. On the back of an astrolabe, you would have all these different sun measurements here. The back is called the black plate, and this sighting tool here is called an alade. Now, The astrolabe helps you measure 360-degree measurements, as well as it works as kind of a planisphere to help you do several celestial problems, kind of an analog computer of sorts. The parts to the astrolabe are broken apart here on the right. You can see the rete here and the rule from the front, the alade from the back. Here is the back plate. Of course, we're seeing the inside of it, and here is the latitude plate. Oftentimes, astronomers would have an entire set of latitude plates depending on the places they were intending to go. These latitude plates are circles that are made with stereophonic projection. So before we get to these exercises, I'm going to stop my screen share to do some things. We talked about the astrolabe, and the astrolabe is actually a flat version of the celestial sphere, which we looked at in the front, and I kind of showed you this one last week. I don't know if you guys can still see it very well, but in the center you have the blue Earth, you have the ecliptic, you have the celestial equator, the tropics, the Arctic lines, you have the prime meridian, you have everything here that is in that armillary sphere we looked at. And you're going to find all of these same things on the astrolabe. There's a website called the Astrolabe Project where you can make your own astrolabe with some of their help. They have the tools to generate the latitude plates, and they also have simulators to which I can kind of show you how the instrument is working. So this is the front of the astrolabe. Around the side here, all of these are hour marks. So this is the prime, this line that you see behind the rete. I'm going to move the rete so you can see it.
You may want to reshare your screen.
Oh, okay. That's good to know. I had forgotten that it wasn't shared. Come on, Zoom. All right. Can we see it now?
Yes, you're good to go.
So here's the Astrolabe Project's website. It's got different things on it of interest to people who make astrolabes, and it's got different models here to where they can paper astrolabes can be corrected. So here's the front of the astrolabe, and all of these numbers here are our markings. So this would be 12 noon. Now I'm spinning around the rete, which has our star backgrounds on it, so that you can see the straight line that goes from top to bottom, and that line is the meridian line. This circle in the center here is the zenith point, the point directly over the observer's head. The circle in the center is the Tropic of Cancer. The circle outside is the celestial equator here, and the very edge of the astrolabe is the Tropic of Capricorn. So you have all of those lines represented. Now this line here that comes from one side to the other is the horizon. This will be our eastern horizon. This will be our western horizon. The eastern point is going to be where the celestial equator touches the horizon, and the western point on the other side will be where the western portion touches the celestial equator, which is the circle inside here. So this here represents our zodiac circle, or our ecliptic, our apparent path of the Earth. And each of these different points represent common stars. We have Rigel, we have Bellatrix, we have Akbar, and so we have several different ones that can be used here, and we have a rule. So this is a lot of things. We also have our black plate here, and we have a shadow box here for determining the sun's elevation and things, and we have these things, these lines here, which are used for determining seasonal hours. But if you're using this rule, we can use it to help solve some simple functions for us. For example, if we wanted to see where on August 1st, the sun is going to hit the horizon, we can align our thing here to August. And we're going to see that the sun is going to be at approximately Leo 9. So we can swap back to the front and look at our ecliptic ring, and we find Leo 9. Okay, now the lines are hard, but here we have approximately Leo 9. So this is where the sun will be on the horizon at approximately the 1st of August. Now, if we want to see its setting location, we just have to turn Leo 9 all the way to our western horizon, and then we will have its setting point there. As well as if we wanted to see the noonday altitude for Leo on the 1st, we kind of go over there to Leo 9, and then there we would have, it's going to be, this is 60, and so it looks like it's going to be around 70 degrees from the horizon on its noontime location for that day. It's as simple for the stars as it is for the planet, for the solar location. You just find the star that you're talking about. Let's go to Sirius here, and we can move it to where we want to, either on the horizon for rising location, for our setting location, or for our noonday location. And all of these hours here are seasonal hours or approximate apparent hours. They're not quite clock hours. Though if you use it right, you usually can get about 30 minutes right with the clock if you are remembering the daylight savings time. So let's go back to our Leo 9 location, and if we put our rule right through Leo 9, it'll tell you the approximate time of sunrise on that day. So that is a basic demonstration of how this thing works. I'm going to stop my screen share again. I also have a hand quadrant. It's used just by, sighting your horizon, finding your elevation, holding your plumb line, and reading your proof. And the quadrants can be made out of simple things like cardboard. When I teach this in class, I usually have a set of these that everybody can kind of walk around and play with, but I also have a couple paper versions that have been made here, and they all work with varying degrees of success. The trick is making sure you have the right latitude plate for your location, because every location needs its own latitude plate. And that's what I had for you all today. Does anyone have any questions, comments, or snide remarks?
I have no snide remarks.
Yes, sir?
I said I have no snide remarks.
Oh, okay.
This would be a cool thing to do at a star party, actually. Have a little workshop where people build their own. That would be a neat thing to do. Anyway, thank you very much for your time. That was really great. So.
Thank you all. I appreciate the chance to present it.
Sure. And we'll have you back again. So that actually wraps up our CFAS meeting, 2 hours. I thank everybody who is still coming out for the Zoom meetings. We appreciate it, and we hope we made it worthwhile for your 2-hour escape from the news channels and everything going on in the world, where we can just focus on some things that we all love together. Also, happy Veterans Day. I did have a note. It's not showing up, but it was like at the top of my paper, and I forgot. But yes, happy Veterans Day, and thank you, veterans, for your service. And I look forward to seeing everybody again next month. And until then, stay safe and keep looking up. Good night.